Hello, Tanya Laird here, and welcome to Part 3 of Lecture 8 of ENGR 231 Engineering Statics. In this part of the lecture, I'm going to go through a couple basic examples of working through 2D problems of static equilibrium when we have some pin, roller, and fixed supports present. So this is just going to be a few basic examples and see how we can apply these. So example 1. Let's start with a very simple beam. And in fact, I'll start with the simplest beam, a simply supported beam. As you remember from part 2 of this lecture, we described a simply supported beam as one that has a pin support on one side and a roller support on another. So this is going to be given, and let's say there is a force of O. Let's do 2 kips, a kip being of course equal to 1,000 pounds. And then let's also say that we have dimensions as follows. We have a dimension of, maybe, let's do this in English units. So let's say this is 3 feet and, 9 feet. Okay, and I want to find the reaction forces on this beam. The reaction forces on this beam. I want to find the reaction forces on this beam. Okay, so there's that. Now, let's say I want to, so let's go ahead and do this, work through this. And like a lot of this, our first step is going to be to create or draw a Freebody diagram. So let's go ahead and do that. And I'm going to call this end A and this end B. So on the left end, I will have an AY and an AX. And on the right end, I'll have simply a BY. So let's go ahead and get these via applying equations of static equilibrium. And this is going to be similar to some of the things we saw last time, or in last lecture when we worked through some examples. But what's different in this particular case is that we are given the supports and we have to go and actually find, we have to recognize that those supports mean that we have a pin roller and what those forces mean, or what kind of forces are present in a pin roller connection, or a pin and roller support, I should probably say. Okay, so first of all, the AX force is going to be simple enough. And again, as I have mentioned before, I just go ahead and usually assume up and to the right for everything. Even though I know this isn't going to be true, I usually just assume up and to the right for everything, even though I know that's often not going to be the case. And if I get a negative number, that just means it's going in the opposite direction to whatever I assumed. So some of the forces in the X direction, I have AX and nothing else, and this is equal to 0 because it's a statics class, and so therefore AX is just equal to 0. Now, I could do a summation of forces in the Y direction, but the problem is I would have AY and BY as unknowns there, so I'm going to avoid doing that right away. I'm going to do instead a summation of moments about point A, and the moments I will have, well, first of all, I just looked at this and realized I have made a terrible mistake. There is a major problem with my Freebody diagram. First, the major problem is that I left out my actual applied force. So that's kind of important, just a little bit important. And I also left out my dimensions, which I really should include in my Freebody diagram. So then I have dimensions of 3 feet and 9 feet. And then let's go ahead and do the sum of moments about point A. Now, again, the reaction forces AX and AY, neither of them will generate a moment about point A, and that is, again, because their lines of action pass right through point A. Now, so what will happen is I will have negative 2 kips. I'll have the moment caused by the 2 kip force times a moment arm length of 3 feet, and it's negative because it is in the it's negative because if I look at rotation about point A, that is going to be clockwise, and that's a negative moment. Then the BY, I'm going to have plus 12 feet times BY, and it's going to be positive because it's a counterclockwise rotation, which means positive rotation. And this is 0. And so then BY, so this is negative 6 plus 12 BY is equal to 0, which means that BY then is equal to 0.5 kips or 500 pounds. So we have By. Now I could go and do a summation of forces in the y direction, but I think I'm actually going to do a summation of moments about point B. And the nice thing about that is that I can use my summation of forces in the y direction as a check to see if I got the right results. So let's do a summation of moments about point B. And actually the math might be just as simple for this particular case. So a summation of moments about point B. And let's see here. Summation of moments about point B. Now, AX and BY, neither of them will generate any moment about point B. And let's say AY. AY is going to be a negative moment about point B, so negative AY times 12 feet, moment arm length of 12 feet, then plus 2 kips, this is going to be a positive moment about point B because it's counterclockwise, plus 2 kips times 9 feet, and this is then equal to 0 because this is statics class, and it's going to be in static equilibrium. So AY then is equal to, AY is equal to 18 divided by 12. If I divide by 3, that's going to be 6 over 4, or that equals, what do you know, 1.5 kips. And this would be upward, and this would be upward as well. And if I want to do a check, I can do, okay, what is the summation of forces in the y direction? Well, I have the negative 2 kip force, the applied one, and then the plus 0.5 kips for By. Well, it looks like the word 2, that's not what I want. Plus 0.5 kips for the By, plus the 1.5 kips for the AY, and all of that indeed does sum to 0. So we see here that often, for simple systems at least, it can be beneficial to solve them using balance of moments, and then you can use the summation of forces in the y direction to simply check your results to see if you got the right result or the right answer. All right, excuse me. Get some water tonight. Okay. So let's see, let's do something a little more involved, maybe still something that's kind of beamish, but ooh, this might be a good one. What if I had a beam where I didn't ignore the, well, I could do that. I'm trying to debate what I want to do exactly. I want to have something, let's see, let me just show you what I have in mind. Let's say I have a beam. Well, not really a beam, sort of. Let's say I have a beam, and attached to this is a little column. So something kind of like this. And I can give it some thickness if we want. But I'm going to ignore the thickness and the dimensions. I'm just going to say, well, let's assume the dimensions, the thickness is, not relevant to, not significant compared to the overall lengths involved. And let's say, this is going to be interesting. Let's say I have, I haven't done one in metric for a while, so I try to mix that up and I try to do in my lectures, use a mixture of, at least in my statics lectures, not civil engineering, say something like steel and concrete design, and do everything pretty much exclusively in English because we use this AISC steel manual and the concrete manual, etc. But and those are all in English units. But in my statics, I try to mix it up and use a mixture of Newtons, yes, but a mixture of metric and English units, or or standard units. Well, not standard units. A mixture of English and metric, so inches and meters, pounds and newtons, etc. So let's just go ahead and do this one. Let's say this is, I don't know, 15 kilonewtons. Nice, good high unit. And let's say this thing is at an angle of, let's give it a weird angle like 20 degrees or something. So I'm going to go ahead and do this one as an ugly decimal because it's going to be kind of ugly anyway because it's at 20 degrees. It's not something that has nice, it's not a nice angle like 45 or 90 or 30 or 60 or something like that. Okay, then I'm going to need the dimensions, both the horizontal and vertical. So I'm going to say this thing has a dimension. Let's say this thing is, I don't know, maybe, 10 feet, or maybe, let's give this thing a length of 4 meters. I know 10 feet is not 4 meters. I just thought that might be nice. And then let's see, and these are all like to centerline dimensions. Again, I'm kind of neglecting the thickness of the member here, of the beam here. When you're doing real engineering, you can't do that, but this is static, so we can be a little bit simpler and reduce things to a little bit simpler state. Okay, and 1 meter. So we have 4 meters in the horizontal and 1 meter in the vertical. And I'm going to ask us to do the same thing. So all this is given. And I want to find the reactions, and let's call this point A, I'm going to call this point B, and point C. I want to find the reactions at point A, forces at point A. The reaction forces at point A. So let's go ahead and work through that. Now, again, like many of these problems, our first step is going to be to draw a free body diagram. And because we're ignoring the dimensions of the thing, or not the dimensions, but the thickness of the member, I'm just going to go ahead and draw this out as a line diagram. So we have this, and I'm going to go ahead and break this up into, I'm going to go ahead and break the applied force up, or the applied force up, into its 2 components. I'm just going to do that to the side, actually. I think that'll be simple enough. So I have the 15 kilonewtons. And I think we can all realize by now that this is 15 times the cosine of 20 degrees. And I'll have the other component, the vertical, which is 15 times the sine of 20 degrees. And I'm just going to go ahead and throw these into my calculator. So 15 times the cosine of 20 degrees. This will come to 14.094. I'll go ahead and carry a large number of decimal places through, or 095 kilonewtons. And for 15 times the sine of 20, that will be 5.130. 5.130 kilonewtons. And on my free body diagram, you don't need to do this, but I know I'm going to have to break this up into components anyway, so I figure why not? I'll just go ahead and break it into components now. So 5.130 kilonewtons in the vertical. I'll just analyze it as if it was 2 independent forces. And then in the x, I'll have 14.095 kilonewtons. 14.095 kilonewtons. Then the reaction forces, I'll have the horizontal restraining force, AX. I'll have a vertical restraining force, AY. And I will have some moment at A, MA. Okay, so this one's actually going to be fairly straightforward, especially once we have our dimensions written down. Let's do that properly. Let's see, this will be 4 meters in the X and 1 meter in the Y. Okay, now let's go ahead and look at this. Okay, so first of all, summation of forces in the X direction. In the X direction, I will have 14.095 kilonewtons, the horizontal component of the applied force, plus AX equals 0, and so therefore AX is negative 14.095 kilonewtons, or 14.095 kilonewtons. That thing is pointing to the left. Then summation of forces in the Y direction. I will have, let's see, I will have AY, positive AY, and then minus, if I can keep from jumping ahead, minus 5.130 kilonewtons. And this equals 0 because this is a statics class. And so then AY, if I solve for AY, is 5.130 kilonewtons. And I have my second reaction force and thus second answer. And so this is 5.130 kilonewtons upward. And then, finally, I want to do a summation of moments. Summation of moments about point A would be the easiest way to do this. And the reason I'm choosing A is that, now, MA still will generate a moment there because it's basically a couple. And you can think of the restraining force, the restraining moments as couples. They, regardless of what point you sum moments about, that moment will still be there. But the nice thing about summing moments about A is that, simply put, the AX and AY will not generate any moment about there. Okay, so I'm going to use each individual force and its perpendicular distance. So I'm going to have MA, the reaction moment. I will have now this horizontal component is going to generate a negative moment about point A because that is a clockwise rotation. So negative 14.095 kilonewtons times a moment arm length of 1 meter. Then this here, the downward component or the vertical component, that's also going to generate a negative moment about point A, and the moment arm length will be the perpendicular distance of 4 meters. So minus 5.130 kilonewtons times a moment arm length of 4 meters. And this equals 0 because this must be in static equilibrium. This must be 0 because it must equal 0 because this is statics class and we are dealing with things in static equilibrium. So MA then, if you throw that into your calculator and move everything to the other side, let's see, 14.095 times 1, well, I don't need to multiply that by 1, plus 5.13 times 4, and I get that MA is 34.62, and the unit is going to be kilonewton meters. Kilonewton meters. All right. 34.62 kilonewton meters. All right, so finally, I think I'm gonna, I want to look at something a little bit more complex, still finding reaction forces, but this is gonna be a little bit more interesting because I'm gonna look at an example where there's actually more than one object involved, and I'm gonna put a rope. I'm going to apply a rope on a body, and see what happens then. Okay, so let's take a look at that. So let's say I have something like this. Now, how do I want to do this? Let's say I have a beam. I'm just going to draw the beam as a line element. Well, actually, no, I think I'll go ahead. And I guess this will be example 3 for this portion of the lecture, so I probably should have titled the other one example 2, but that's okay. So I'm going to have let's do not quite a simply supported beam, but sort of like a simply supported beam. And I think up here I'm going to have a little part that juts out like that. This is going to be a fun one. And I'm going to put a pulley on this. It's going to be a nice ideal pulley, so we don't have to worry about pulley friction or anything like that. And then it's going to continue on like this. And there will be another pulley here. So a pulley and a pulley. And then I'm going to have let's say a pin here and a roller joint there. Or a roller support there. So I have a pulley, a pin, and a roller holding this thing up. Then I'm going to do something really fun-ish. Maybe I want to do that in red. I like to. I'll show where the surface. I'll show where this thing kind of has a surface that goes like this, so I can hang something below that. And then let's say I have a rope, which I think I'll make it purple. And let's say it's kind of like this. It comes up, it goes around the pulley, then it comes down here, goes around the pulley again, and then comes down. And it's attached at this point here. So it's just attached there. Now, I'm going to give us the dimensions. The dimensions here are, let's just make this, what might I want to do? Let's say this is 2 feet, 4 feet, and 3 feet. 2 feet, 4 feet, and 3 feet. And attached to this then is a 10-pound weight. And I want to find the reactions at each point. So let's go ahead and do that. The reactions then at point A and B. The reactions at A and B. So let's consider that. And how can we handle something like this pulley? So this is going to be a little bit tricky, but it hopefully won't be too bad. Okay. So we have to sort of think through this very carefully. And think about how the tricky part is actually this location here. And if you think about that pulley is that rope, or I should say, is not going to be able to generate any kind of horizontal force, or sorry, vertical force at the edge right here. The rope's going to come here and then immediately pull around. So it may be able to exert a force like this, but it's not going to be able to exert a downward force once it passes the once it passes the midline of the pulley. But it will be able to exert a force like this. Anyway, one of the properties of the cable is that it's going to have a constant tension anywhere through it. So if I were to isolate just the weight, I could see very easily, if I had a tension here, that the tension is going to be equal to 10 pounds. So that's not going to be too concerning, and it simply has a tension of 10 pounds. And so, but because these are ideal pulleys, the pulleys can change the direction of the force, but they can't change the actual amount of the force. They can't change the value of the force. In terms of reactions, well, something really interesting happens. So let me go ahead and draw a free body diagram out. And I'm going to draw this thing as a line element here. And the reactions, the reaction forces, I will have AY, AX, and BY. And then, let's see, what else? Well, again, this is not going to, you might be tempted to put a downward 10-pound force here, but we actually can't do that. And again, the reason for that is because, as I described previously, that pulley is not going to be, that cord is not going to directly apply a 10-pound force to the edge of that pulley there, because it's around the side. However, what there will be is a 10-pound force basically being applied. Well, let's think about this. I know there's going to be a 10-pound force basically applied like this. Let's see, is that going to make sense? Actually, we may not be able to say that. I think we actually need to isolate those joints before we say that for sure. One way to think about this is if we want to figure out what kind of force is applied by the pulley, this may be a bit more complex than I'd wanted to get into. This is almost getting into frames and simple machines. So we could abandon this, but I don't want to. So I want to figure out what kind of actual external forces are being applied to this. So let's go ahead and take a look at that. Let's just isolate just this pulley here. Or let's isolate this portion of the cord here. So I have a cord. Basically, I have a cord and another part of the cord here, and the pulley is going to apply a horizontal force basically to it. Or I might ask, what kind of force does the pulley need to provide in order to keep this thing in equilibrium? So basically, I have a 10-pound force here, and I have a 10-pound force here. So actually, I need to think. I've needed to think through this thing a little bit because it's a little bit tricky when I think about it. And so maybe it actually can apply a vertical force to this now that I'm thinking about this. So what I need to say is, okay, well, first of all, I need to isolate this pulley and say, okay, well, what kind of X force is going to be applied to this pulley and what kind of Y force. So there's going to be some sort of Fx and some sort of Fy. And in fact, maybe I'll just call this point C and the other one point D. So this is point C and point D. So I'll call this force. And again, what I'm basically drawing out here is this is a piece of the rope right here, right at the point where the pulley contacts the rope. So it's more like I'm doing a point particle equilibrium on just that slice of the rope there. So I have a Cx and a Cy. So the first thing I'm going to do is just a equilibrium on just that piece of material, of that rope. So summation of forces in the y direction equals 0. Or just summation of forces in the y direction ultimately equals 0, but I want to write some things for it first. Or actually, maybe I can even do in the x direction. This is going to equal, let's see. This is going to be, and I need the, actually, let's just say I would also need it to be given the height of this thing. So let's say this is 2 feet as well here. 2 feet as well. Incomplete problems are no fun. Okay, so sum of forces in the x direction, and I needed that to get to put the force triangle down. This was 2, 3, and then that would be square root of root 13, basically. Root 13. Square root of 13. So summation of forces in the x direction, I'm going to have negative 10 times, that's going to be 3 over root 13. 3 over root 13 plus Cx is equal to 0. Negative 10 times, that's basically the x component of that 10-pound force, plus the Cx. And so Cx then is equal to 30 divided by root 13. And then if I do a summation of forces in the y direction, I will have 10, this force here, times, I'm going to look it a little further over. Summation of forces in the y direction, I'll have 10 times 2 over root 13 for the y, to get the y component, and then plus cy, and then minus 10 equals 0. Minus 10 equals 0, and I think I'll just go ahead and do these as ugly decimals because I'm feeling lazy. 30 divided by the square root of 13, this comes to 8.321 pounds in the x direction. And then the y, the cy is going to be then, that's 10 minus 20 over root 13. 10 minus 20 divided by the square root of 13. And that comes to 4.453. 4.453 pounds. Okay, now here is where we need to apply equal and opposite forces. So again, this represents a cut of a piece of rope that is basically the piece of rope that is in contact with this. Actually, let me check something really quickly. Let me get the magnitude of this. Nope. Okay, so yeah, it actually isn't something that we could just figured it out. So, okay, so this problem it actually is turning out a lot more complicated than I intended, but that's okay. It's still an interesting and useful example. So again, the rope, that piece of rope is being pushed to the right and upward by whatever reaction force is present at that pulley, or not reaction force, but whatever force is present at that pulley. And so, in this case, if the pulley is being pushed, if the rope is being pushed to the right and upward, the pulley must be being pushed. Or in other words, the rigid body here, the frame, must be being pushed to the right, or to the left and downward. So I can just replace that force. I'm just going to replace that force generated by the rope as a 8.321 pounds to the left, and not an upward force, but a downward force of 4.453 pounds. 4.453 pounds. Next, I want to do the same thing on for the top pulley, and I'm going to isolate the piece of rope that is right where the top pulley, just that piece of rope where it meets the pulley, the top pulley. Okay, so let's go ahead and isolate. I'm just isolating this piece of rope here. And again, this may be able to transfer some force. The pulley may be able to transfer some force into in the X or Y direction there. And it's going to be, let's see, so let's isolate that point, just that little piece of rope, and I will have two 10-pound forces, and they would cancel out, except they're at different angles. And then let's say I have a dx and a dy. I'm not sure what direction they're going to be, so I'm just going to assume up and to the right for now. And a 10-pound force here. Again, it's an ideal pulley, so the force just continues on through. 10 pounds and 10 pounds. And the angle of this, let's see, this is going to be a 4x2, or actually 1x2 if I can just divide both by 2. 1, 2, and then that would be root 5. Root 5. And then this is going to be the same 2, 3, root 13. Root 13. So now I'm going to do the summation of forces in the x direction on this thing. Just on that, again, I'm doing a point particle analysis on just the bit of rope that's at the top of the pulley. So yeah, this is definitely more involved than I thought I'd want to do, but okay, it's fine. It still illustrates some nice concepts. So I'm going to have dx minus 10 pounds times I want to get the horizontal component of it. That's 2 over root 5. Then plus 10 times 3 over root 13. 3 over root 13, and this equals 0. And therefore, dx then is going to be 10 times 2 divided by 5, or square root of 5. My root somehow disappeared. Divided by the square root of 5. And then plus 10 times 3 divided by the square root of 13. So 10 times 2 over root 5 plus 10 times 3 over root 13. Oh, actually minus, sorry about that. They're going in opposite directions. So I need to put a minus on the 10 over 2 root 5, or 10 times 2 over root 5. So let me check this. 10 times 2 over root 5. Again, I'm just entering this in my calculator as I go. 10 times 3 over root 13, and I get, well, basically dx minus 0.624 pounds equals 0. So dx is then 6.24 pounds, or sorry, 0.624 pounds. And that's to the right. But again, this is the force that is being exerted on the rope, not the force that the rope is exerting on the frame. And then finally, I'm going to come over here for the y. Summation of forces in the y. I'm going to have dy. And then, let's say, minus 10 times 1 over root 5. Minus 10 times 2 over root 13. Equals 0. So minus 10 times 1 over root 5 minus 10 times 2 over root 13. And then dy will simply be 10 over root 5 plus 20 over root 13. 10 divided by the square root of 5 plus 20 divided by the square root of 13. And I get a dy of 10.02 or 019. Let's just do 3 decimal places, carry through. 019, not kilonewtons, pounds. 10.019 pounds. Does that make sense? Well, actually, that does make sense. That could certainly make sense. Okay. But I will double check. 10 times root 5. 1 over root 5, 10 over root 5, yep. And then 20 over root 13. That is correct. So basically what I have is, I see what I actually assumed. Again, I just sort of naively assumed everything was to the right and an upward positive, but this one actually turned out correct. So that rope is being pushed, that little bit of rope is being pushed to the, if it's to remain in equilibrium, it must be being pushed by that spite support, its pulley, a net amount of to the right and upward. Then, let's see, I want to then apply those forces to this diagram, and I'm going to apply them in their opposite directions. So now the dx will go to the left, again, equal and opposite forces. I calculated the forces that are holding the rope in place, but that's the forces being exerted on the rope by the pulley. What I need to draw here is the opposite. What kind of forces are being exerted, what kind of forces are being exerted on the frame, the opposite. So I'm going to have the x, which is 0.624 pounds to the left, and a downward 10.019 pounds in the y. 10.019 pounds. And let me go ahead and get redraw the dimensions on here. This is going to be, well, now since I need one other thing, and that is the force here. And let me just go ahead and break that into components. I need to worry about, let me call that point E. That's the other thing I need to worry about. And E here, well, this one's a lot simpler because we just have, maybe I'll just hide it over here. E, well, all I need to worry about here, I just have two things basically. I can just directly break that into its horizontal and vertical. The horse of that applied 10-pound force, there's a 10-pound force just connected there. So that is 10 times, let me just draw it out first actually. I have this 10-pound force, and its dimensions basically are 4 root 2. So the same kind of thing as before. It's basically a 2 to 1, and that's root 5. So that basically means that I have in the x direction, I have, let's say, 20 over root 5. And in the y, I have 1 over root 5. 10 over root 5, because we have to multiply by 10. Which this comes to, and this comes to, again, I'm just going to do this as ugly decimal. 10 divided by the square root of 5. This is 4.472 pounds, and then 20 divided by the square root of 3. And this comes to 11 point, wait, something was, let's see. Oh, I divided by root 5. No wonder I was getting a little weird. Or I divided by root 3. Sorry about that, not root 5. I divided by the wrong denominator here. That's root 5, not root 3. So 20 divided by root 5 is 8.944 pounds. So I now have a really messy Freebody diagram, but I'll go ahead and break this into its components and draw those on the diagram. And I don't need to apply the equal and opposite forces to this one, because again, in this case we are basically dealing with the force already taken into account. So I'm basically just saying there is a 10-pound force being applied to this, the tension force, and we already know the angles of it, etc. So this is going to be then the dx. Where was that? That is 8.944 pounds and an upward force of 10.019 pounds. 10.019 pounds. Now, I need to transfer this to the next slide, so I think I'm going to do that. Let's see here. What's the most effective way to do this? Okay, that's fine. I think I can just copy it over. So I'm going to redraw my Freebody diagram and then use this for calculations on this page. So, let's see, actually I might give myself a little more room here. And I'm going to put my reaction forces first. I have AX and AY. AX and AY. And I have BY here. And then I'm going to show all the forces that are applied to this. 0.624 and so let's say 0.624 to the left, 0.624 to the left, and 10.019 downward. Then at this point, 8.944 to the right, 8.944 to the right, and upward of 10.019. Let's not 10.019. Sorry about that. That's not quite right. That was 4.472. That should say 4.472. Sorry about that. Because I knew immediately that something was wrong there, because they can't be more than 10. They're components. So 4.472. 4.472 pounds here. And then at the end, a force to the left of 8.321 pounds. And a downward force of 4.453 pounds. And then let's go ahead and write down the dimensions. Let's say I have, it's going to be 2 foot, 4 foot, and 3 foot. 2 foot from here to here, 3 foot from there to there, and 4 foot from there to there. Whew, what a mess. Okay, and that's 0.624 there. I just showing those are separate arrows. Okay, so next, now all that's really is left is to work through the equations of static equilibrium. So let's go ahead and just do this. Now I could do this all with balance of moments, but this is taking long enough, so I think I'll just jump to sum of forces. Summation of forces in the x direction. I'm going to have AX, let's see, plus 8.944 minus 0.624 minus 8.321. And all of this is equal to 0. And therefore, if I solve for AX, I will get, let me just do this in my calculator. Let's see, 8.944 minus the 0.624. And then minus the 8.321. And what do you know? I get 0. Interesting. So that actually is a sign that I did something right. It's not a weird error. That actually is a sign that I did something right. Then, let's do the summation of forces in the y direction. The summation of forces in the y direction, I am going to have, well, actually, I don't want to do that just yet, because I'm not going to have, I don't want to have by and ay in the same equation. So summation of moments about a, let's go ahead and do that. All of the, let's see, this horizontal force won't have a moment there, this one won't have a moment there, but an ay and ax won't, but by will. So let's say I have a by positive moment, because counterclockwise times moment arm length of 5 feet. Then I'll have the plus 4.472 times its moment arm length of 2 feet from point A. 2 feet from point A, 4.472 times 2 feet from point A. Then I'm going to have a positive moment with a moment arm length of, and this dimension here was, the vertical was 2 feet. So I need to worry about the moment of that, the 0.624, also positive. 0.624 times moment arm length of 2 feet. And then minus 10.019 times a moment arm length of 5 feet. Plus here, let's see, plus by times moment arm length of 5 feet. And then finally, minus 4.453 pounds times a moment arm length of 9 feet. Okay, let me double check this. Let's see. That looks like a lambda or something, AX. So the 4.472 is positive with a moment arm length of 2 feet. The 0.624 is positive with a moment arm length of 2 feet. The 10.019 is negative with a moment arm length of 5 feet, by is positive with a moment arm length of 5 feet, and the 4.453 is negative with a moment arm length of 9 feet. Okay, I'm going to throw all this mess in my calculator and solve for by. All right, so by, the 4.472, let's grab that, times 2, plus 0.624. Let's get that. Where are you hiding? There you go. Times 2. Then, actually I might do this in pieces. So 5by, it's going to make the calculations a little bit simpler and for you to follow along at home. 2 times 4.472. So I get 5by plus 8.944 plus the 0.624, the 0.624 times 2 feet, times 2 feet, and that's going to be plus 1.248, and then minus the 10.019, 10.019 times the moment arm length of 5 feet, minus 50.096. And I still have the 5by, so that's not changing. Actually, I made a slight mistake. I wrote the by twice. That's okay. We caught our error. Minus 50.096, that is the moment, that is basically 10.019 times 5. And then the negative 4.453. 4.453, where are you hiding? There you are. I'm sorry, basically when I say where are you hiding, I'm asking myself where in the calculator they're hiding. Because I'm just copying and pasting as I go. In my calculator anyway. Negative 40.077, and the units here would be pound feet per moment, but that's not really that important. 0.077, so 5by, the 8.944, which is positive, the 1.248, which is positive, the negative 50.096, which is of course negative, and the negative, and this, the 4.453 times 9, which is also negative. And then I can just get by directly, add this all up, move it to the other side, and divide by 5. So let's see, 8.944 plus 1.248 minus 50.019 minus the 40, and then I'll bring it over to the other side and divide by 5. And I get that by is that's going to be 15.996, and that looks pretty close to 16 pounds to me. But we'll see. 15.996 pounds. Then I'm going to do the summation of forces in the y direction. Summation of forces in the y direction. This is going to be AY plus 4.472 minus 10.019 plus the BY, which is plus 15.996, and then minus the 4.453 equals 0. And those should be the only vertical forces. The AY is positive, the 4.472 is positive. The minus 10.019, well, that's the 10.019, that's negative. The BY is a positive 15.996, it's already baked into there, and the minus 4.453. And let's go ahead and get this. I'm just going to do 4.472 minus 10.019. Plus the 15.996 minus the 4.453. Where are you? There you are. So in my calculator, I'm checking those entered correctly. 4.472 minus 10.019 plus 15.996 minus 4. And AY then. Okay, let's see. So basically, this comes to AY plus 5.996 5.996 then is equal to 0. So AY is actually a downward force. It's a downward restraining force of negative 5.996 pound, just pounds, not pound inches, just pounds. So this one is upward and this one is downward. Now, I did want to mention there's something really interesting here. Notice there the actual AX is 0. In other words, this doesn't need any horizontal force to actually hold it in place. And the reason for that is that we have a lot of what are effectively internal forces here. This cable is, it'll end up putting this in compression, but if I were to isolate the entire thing, imagine isolating the entire thing, like cutting across the entire thing, including the rope, and treating the whole thing as a single rigid body. If I were to ignore these are internal forces, and we could have actually done that, solved this problem just by ignoring them, because all we're after is the reactions. And if you have internal forces present in a body, they must cancel out. So that's why, even though we do have some internal forces of tension here and here, they cancel out when you add them all together, and you ultimately end up with no reaction force on joint A, or in the X direction. Then what about in the Y direction? Well, we have an upward 15.996 and a downward, actually that's 5.996 pounds. And if you notice, what do those add up to? Those will add up to a total of 10 upward, which is exactly opposite to the 10 pounds downward that we got. So we actually didn't need to do all those things with those pulleys. I just wanted to demonstrate to be sure and for you to see that if you take something, if you cut in real internal forces, the overall stability or the overall forces needed to hold the entire body together do not change. And that'll be more important, especially when we get to, remember, internal forces and things like shear and moment and axial force, etc. So really, at the end of the day, it all just comes down to a single, you still could treat this as a single rigid body, cutting out basically along here, and just ignoring the internal forces, because they do actually all cancel out. The internal forces all cancel out. And the reason for that is that internal forces basically always have to cancel out. Only external forces are what will contribute to static equilibrium in terms of restraint forces. It's kind of like trying to push yourself if you're in a boat. A very similar analogy would be like, imagine if you're in a boat on the water. The only way I can make myself move if I'm sitting in a boat is by having a motor or something, or maybe if I'm doing maybe I'm using like a paddle. I sit here and paddle along the water, and I'm doing that, but I am able to move in the water because what I'm doing effectively is I'm interacting with matter outside of my object that I'm joined to, the boat. And so the paddle is the force from the paddle is an external force. But what if I were to sit in the boat and like try to, brace myself against it by pushing on this left end with my hands and the bottom end with my feet? I'd have to be a fairly short boat to do that. But I wouldn't be able to move myself forward and backward. There would be forces produced by that on the material of the boat in terms of strain and stress, but me simply pushing on the boat while I'm standing in the boat or attached to the boat isn't going to make the boat move forward or backward. The only way I can do that is to interact with matter outside of the system, and that's very similar to what's going on here. Anyway, I think that'll do it for this portion of the lecture. This ended up being a bit longer and a bit more involved than what I planned, but I think it was hopefully illuminating, and hopefully you all learned some things. Let me know if you have any questions, either in class or via email, or here on YouTube if you wish. I'll see you all later for a quick part 4 to this lecture, and as always, thank you.